So question number 2. Okay. Find the normalization constant n for this given array function. So what to do? The normalization constant we need to find. So normalization condition is psi get brass I get psi equals to 1. That is, if we write it in terms of integration, minus infinity to plus infinity, psi star psi d tau equals to 1. Okay, so here psi is given as this, so minus infinity to plus infinity psi star psi, that is mod of psi square into dx equals to 1. And if we equated this and then apply the formula here, so you can substitute x minus x naught as t, that is dx will be dt, and therefore we get minus infinity plus infinity e to the power minus t square by k square. Okay, so here this is gamma function, so here we use the trick that is for direct formula here, minus infinity to plus infinity t to the power n e to the power minus say b into x to the sorry let's take it as x to the power n e to the power minus b x to the power n into dx. It will be 2 into, that is 2 into 0 to infinity. Okay, it is better to write 0 to infinity. Okay, sorry for that. 0 to infinity, this it will be 1 by m, then gamma n plus 1 by m divided by, this is the gamma function, and divided by b to the power n plus 1 by m. Okay, so now we do know gamma half equals to root pi. Okay, and gamma n plus 1 equals to n factorial. So here we substitute this, and after that this is t square, so it will be, it is even function, so we can write twice of this as integration 0 to infinity, and then use this formula here. After using this we get k value, sorry n value is this. This is the formula. Okay, so this is the normalization constant for this problem. Now after that, obtain the Fourier transform of psi of x. Okay, so psi of x is this. We calculate n value here, and what will be the Fourier transform? Now this is the general expression of Fourier transform, that is 1 divided by root over twice pi h cross minus infinity plus infinity psi of x e to the power minus p by h cross into x into dx. This is the general form of Fourier transformation. So now we find the Fourier transform of psi of x in what? uh, what is the transformation? That is the real space to k space. Okay, but we find k space but in p space, that is already h cross k is here. Okay, that's why this form looks like okay. So 1 divided by root over twice by h cross times minus into plus into psi of x e to the power minus iota p divided by h cross into x into dx. Okay, and substitute these things. So after substituting again x minus x naught we take as t here, and substitute these things. Okay, and then combining this two term, combining these two term, and this is the constant term here, e to the power minus iota p by t sorry p by h cross into x naught. This is constant term, x naught is constant, so we can take it out from integration. Okay, now after that minus infinity plus infinity, if we common out 1 by t k square here, uh, that's why we multiply 2k square with p by h cross term. Okay, and after that we rewrite these things in square format, and subtract this term since this term is not included here. Okay, and after that same formula we can use here as gamma function. Okay, since it is gamma function, then we get this result ultimate. So phi of p, that is the Fourier transform of psi of x, will be this. So in that we calculated earlier, that is n equals to uh, what n equals to 1 divided by 1 divided by k into root over pi to the power half. Okay. So it also we can write this as pi k square to the power 1/5. Okay. So this is the n value. Now what will be the next part of this question? So taking the ground state wave function of hydrogen atom, this is the ground state wave function of hydrogen atom. Okay, and a naught is the Bohr fast radius, so that the most probable position. So most probable position is a naught. A naught we have to show the most probable position for electron is a naught, and so that the expectation value of R is greater than the most probable value of R in the ground state. Okay, no problem. So what is the ground state of the hydrogen atom? This is the ground state hydrogen atom. So we can write this in terms of 1 divided by root over pi n naught cube. This is the general form. Okay. Uh, so now what will be the this is the general form, that is if you are given that is the ground state in terms of like UNR or UNL. Okay, so what will be the probability distribution corresponding to this state? Okay, the probability distribution is written as DNL is given is written as R squared times UNL square. Okay, this is the probability distribution DNL. So here ground state, that is n equals to 1, l equals to 0. So corresponding this state, the probability distribution function looks like R squared times U10 square. Okay, so this is the probability distribution. Now at most probable position, the derivative of probability distribution function at that point, most probable point, will be 0. Okay, so at first we need to differentiate this term in terms of R, and then equate it to 0. Okay, from here we can find the most probable position, that is most probable position is Rm equals to a naught, Bohr radius. Okay, so proved. Okay, and next term is we need to find the expectation value of R, and after that we need to show expectation of Rn, sorry, expectation of R is higher than the most probable value. Okay, so what is the expectation value in bracket notation? The expectation value of R will be psi R psi. Okay, so in integration from minus infinity to plus infinity, psi star R psi. Okay, so psi is what? Psi is 1 by root over pi n naught cube e to the power minus r by n. So if we take the psi star, it will be same, since psi is a real quantity. Okay, so simple mod square, simple square. Okay, that will be 1 by, if we take psi star psi, then it will be 1 by pi n naught cube e to the power minus twice r by n naught. Okay, after substituting the value, there is also r here 1. Okay, so here d tau is basically 4 pi r square into dr. Since it is spherical, that's why we use d tau here. Okay, that's why we use d tau here. But in the previous problem, uh, the function is unidirectional function, because size depends on x only. That's why we use dx here. But in general, we need to use minus infinity to plus infinity psi star psi into d tau, where d tau is the volume. Okay, so in case the, for hydrogen atom we need to use d tau. D tau is the volume, so it is nothing but 4 pi r square into dr. Okay, so using this and using same formula gamma function to arrive this step, and after that we get the expectation value of R ground state will be 3 n naught, which is higher than n naught. Okay, so the expectation of R is higher than the most probable value. Okay. Now next problem from harmonic oscillator. What is the value of x for which probability density corresponds to the ground state wave function for one D harmonic oscillator maximum? Same things, psi, then mod probability density, it will be maximum for what? X equals to 0 point. Okay, how does this compare with classical? Okay, so we know general expression of harmonic oscillator wave function, that is psi n of x equals to uh, what alpha, I think if we write alpha as the form, that is in general alpha square by pi to the power 1 by 4, okay, then 1 divided by root 2 to the power n into n factorial, then harmonic polynomial alpha x, then e to the power minus alpha square x square by 2. Okay, so for ground state n equals to put n equals to 0 here, then we arrive this form. Okay, okay. Now, what is the probability density? So probability density will be mod square. Okay, so this Gaussian function will be maximum when it achieves the maximum value when x equals to 0, x equals to 0. When x equals to 0, it gives the maximum value, that is m omega pi h plus to the power half. This is the maximum value. Okay, that's why at x equals to 0 it gives the maximum. Okay, so the ground state wave function oscillator, the probability density is nothing but psi star cell. Okay, so it will be maximum at x equals to 0. That is, at origin, if we draw the potential for harmonic oscillator, at origin the probability density will be maximum for the quantum oscillator. In case of classical oscillator, the probability density is maximum at the end point. Okay, at the turning point x equals to plus minus a, at maximum amplitude the probability density will be maximum. So this is the main fundamental difference between classical oscillator and quantum oscillator. Okay, so in quantum case it's maximum at center, so in quantum classical disagreement. Okay, okay. Next question is harmonic oscillator as a time dependent wave function is given as this, time dependent x position and t also. So fast excitation state psi 0 is the second, sorry, ground state. This is the GS and this is the fast excited state. Okay, so find the expectation value of the energy in this state. That's simple, very easy. So corresponding for harmonic oscillator in general, n plus half h plus omega. So this is for ground state n equals to 0. So E0 equals to half h plus omega, and this is for the fast excited state n equals to 1 here. So this is the EG, and if we fast excited state, that will be 3 by 2 times h plus omega. Okay. Now the expectation value is nothing but summation lambda I then mod of c square. So c is called here the c is the coefficient of this wave function. So mod c square is called the probability amplitude. So this mod square and lambda is the corresponding eigenvalue eigenvalue of the corresponding state. So lambda I means corresponding state. So there are two states, ground state and fast excited state. So lambda 0 and lambda 1. Okay, so therefore we get this, that is mod of c square, so 1 by root square, then e naught plus 1 by root 2 mod square e1, then substitute this value, we get this thing. So this will be 4 by 2, that is twice h plus omega and 2. So what will be the this will be the expectation value of the energy for this state. Okay, and next question, so find the minimum uncertainty product of del x and del px. We know that del x and del px, the minimum uncertainty product is nothing but h plus by 2, but we have to find the minimum uncertainty product of x. These are called canonically conjugate. Okay, canonically conjugate quantity. So but we have to find the uncertainty product for nth energy eigenstate for one dimensional harmonic oscillator. Okay, let's see. So for harmonic oscillator, we know the kinetic energy is nothing but p square by 2 m. Okay, and potential energy v of x half m omega square x square. Okay, now here the total energy, the total expectation value of energy, that is the total energy for harmonic oscillator for 1D is distributed equally in kinetic and potential. Okay, that means expectation of kinetic energy and expectation of potential energy equally distributed. Okay, the total energy equally distributed among kinetic and potential. Okay, so therefore we get expectation of kinetic and expectation of potential will be expectation of E times half. Okay, now we know the for harmonic oscillator in 1D expectation is given as n plus half times h plus omega. So what will be the expectation of k, that is half times of this, half times of this, similar way for potential. Now we know that kinetic is nothing but p square by 2sm, so p square by 2sm. So what will be the expression of p square in any state, say nth state? Expectation of p square will be m omega h plus times n plus half. Similarly, what will be the expectation of x square in nth state? That will be h plus by omega into n plus half. Now we have to find the deviation, we have to find the variance, we have to find the variation in del x. Okay, so del x will be standard deviation root over x square, mean of x, that is what what is what is called root over sorry mod of that is uh, expectation of x square minus expectation of x per whole square. Okay, so after substituting this we know that the expectation of x and expectation of px for harmonic oscillator is 0. Okay, expectation of x and expectation of px will be 0 for harmonic oscillator due to odd function. Okay, so since expectation value is always real, that's why 0 only for p, and due to odd function x is 0. So after substituting this calculated value, expectation of p square and expectation of x square, we easily get the del x and del px. Okay, so what will be the minimum product of del x and del px? We get h plus times n plus half. So minimum will be when n equals to 0, since it is harmonic oscillator, n runs from 0 to infinity. Okay, so minimum product will be h plus by 2. Okay, okay, now move to this next question. So this question given as an internal state of hydrogen atom, NLM, n principal quantum number, azimuthal quantum number, ml magnetic and spin. Okay, so this is the notation state, this is the notation of state. Okay, now psi is given in terms of this. So initially we have to normalize this. So what will be the normalization condition? The normalization condition is psi equals to 1. We can also easily find this, that is this is C1, this is C2, this is C3. So normalization, we have to find the normalization. Now we have to normalize this wave function. Okay, that is another condition is mod of ci square equals to 1. Okay, so if we divide mod of c square uh, both function, then we get normalized wave function. Okay, so this is the form. So this is ci square, ci is okay, we get 9 and divided all the expression uh, with root under 9, that is root over ci mod square. Okay, with this term we get the normalized wave function. This is the normalized wave function. Okay, so after that find the expectation of energy, angular momentum square and projection of Lz. So simple. So energy is nothing but 1 by n square, variation with n 1 by n square with a minus 13.6. Okay, so for the first state that is this what is this, what is the value of n equals to 2 here, n equals to 3 here, n equals to 2 here. Okay, so ci square into lambda I, so ci is nothing but here 1 by 9. Okay, 1 by 9. So sorry, for the first state ci square will be 4 by 9. For the second state ci square will be, this is mod of this, mod of ci, so mod of iota minus iota will be 1. Okay, so 1 divided by 9. For this state it will be 4 by 9. So these are the things. So second state, third state and second state again. So after substituting this we get these things. So for second state this is the energy on by L square variation give the energy expression of this. Now we know that if we operate L square on state psi element, we get L square, that is L into L plus 1 into H cross. This is Newton, sorry, L square, so therefore it will be squared L square, that is L into L plus 1 into H cross square, this into psi element. So this is the expression H cross square L into L plus 1, and using this we get L square is this. Similar way, if we operate Lz on psi element, we will get M H cross psi element. Okay, so here we also find Lz here. Okay, in similar way, this is the Lz value. After that, we have to find what is the probability that spin projection measurement in z direction is state to deal spin up state. Okay, half H cross the probability, sorry, half the probability is half. So okay, so here state is given is this. So we have to find the probability for half state, ms equals to half. So this for ms equals to half, and this is the ms equals to half. So what will be the probability? So mod of root 9 square 2 divided by plus this is minus 2 divided by root over mod square. So this is the probability, that is 4 by 9 plus 4 by 9 is 8 by 9. So this will be the probability. Okay, so this will be the probability. Okay, now question B. Write the formula of the fast non-degenerate pattern correction. This is very simple question. We can then we will write it as this. So first, if we have a system, uh, it has a Hamilton, it has a energy value, that is the total energy equals to kinetic energy plus potential energy. So if we consider the Hamiltonian of that system, of that pure system, of the unperturbed system is H naught, and if we apply a Hamiltonian on that system indicated as H prime, and we consider a lambda, which is a factor here between, in general it lies between 0 to 1, then the exact then the total Hamiltonian of that system will be unperturbed Hamiltonian plus lambda times H prime. This is the perturbed Hamiltonian. Okay, so what will be the first order correction in energy state? The first order correction is nothing but the expectation value of perturbed Hamiltonian in the ground state, in that state. Okay, in the ground state. So when if we find if you want to find the correction in n state, then it is simply en of 1. So this is the first order, this indicates the order of correction, this is the first order. It will be n, and this is the, if we take the ground state, h prime, then n. So this is the correction in the energy state. Okay, n0 is this is earlier I said this is the order of correction. So n0 means it is unperturbed state. Okay, this is the nth state obviously, but 0, the subscript indicate the perturbed or unperturbed. It is 0 means it is unperturbed state. Okay, unperturbed eigenstate. H prime is the perturbation which is externally applied. Okay, also we can this question. So this is basically theoretical question. What is meant by the identical particles in quantum system, and symmetric asymmetric wave function? What is the consequence of symmetry and asymmetry? Okay, so identical particles are nothing but particles that are completely indistinguishable. Okay, we cannot distinguish the particle. Okay, so if you have two ball in same size, two red ball in same size, in same shape, we cannot disintegrate, we cannot distinguish them. Okay, So that type of particle are called identical particle from each other in every physical aspect: mass, charge, spin, etc. Okay. No experiment can tell one apart from the other. Okay, these are called identical particles, like quantum particles: electrons, protons, neutrons, photons. Okay. And if we if if you have two particles, two identical particles, total wave function is x1 and x2. That is, the x1 is the position and x2 is also position. Two of two particle remain unchanged in magnitude. That means if we if I said the position of the first particle is psi of x1 and position of the second particle is psi of x2, so if we replace the position of them, that is, if I place the second particle in the place of first particle, that is psi of x2, and second particle in first particle in the second particle, first particle is placed in the in the position of the second particle, that is psi of x. Also you can use superscript. So this is psi 1, this is psi 2, this is 1. So here it is said that the probability amplitude will be same, that is the magnitude will be same. So psi of x1 x2 mod square will be same as psi of x2 x1 mod square. Okay, so this implies psi of x1 x2 equals to plus minus psi of x2 x1. Okay, now for symmetric wave function, symmetric wave function means this the wave function will be same. If we change the position, then wave function will remain same. That is, psi of x1 x2 will be psi of x2 x1. Okay, these are called the symmetric wave function. So symmetric wave function, bosons, the indistinguishable particle bosons are follow these things. Okay, bosons are follow this type of wave function. So used for bosons, basically integer spin. Bosons can occupy same quantum state. Okay, leads to Bose-Einstein statistics. Okay, basically this type of particle which are follow the symmetric wave function, they can be can be studied under BE statistics. Okay, and for antisymmetric wave function, antisymmetric wave function means psi of x1 x2 will be minus of psi of x2 x1. Basically they are fermions. If two fermions are in the same state, then we get 0 psi. I have fermions are follow the Pauli's exclusion principle, lead to Pauli exclusion principle. No two fermions can occupy it in the same state. They follow the FD statistic, Fermi-Dirac statistic. So these are the some consequences for symmetry and asymmetry wave function. So for property quantum spin, bosons have and integer spin, fermions half integer spin, like half, 3 by 2, 5 by 2, and so on. And this is for 0 1 and so on. Allowed same state, yes, same state allowed. They can stay more than one in same state in a single state, but fermions cannot stay due to Pauli exclusion principle. Example: photons, helium atoms, they are bosons. Fermions are electrons, protons, and neutrons. Okay, quantum statistics. So bosons uh, follow the Bose-Einstein statistic, and fermions follow Fermi-Dirac statistic. But this is some consequence of symmetry and asymmetry wave function. Okay. Now next question is parity operator. P is given as this. So we have to show it has two eigenvalues and find the eigen function for each eigenvalues. Okay, so this is given parity operator. So suppose if we operate psi of x and we get an eigenvalue lambda. Okay, we get an eigenvalue lambda. Now here given, if we operate parity p on a on a function psi of x, then we get psi of minus x. Therefore we get psi of minus x equals to lambda times psi of x. Okay, okay. So again, if we apply p parity on psi of minus x, then similar way If we compare both things, then we get psi of x. Okay, so ultimately what we get psi of x equals to lambda square times psi of x. Okay, therefore lambda square will be plus 1, sorry, so lambda will be plus minus 1. So these are the eigenvalues of parity operator. So what will be the eigenfunction? So eigenfunction, even function psi of minus x equals to psi of x if it is even, for psi of minus x equals to minus psi of x. So these are the solution. Thanks for watching.